going to talk about the design search autocomplete system today. So what is the search autocomplete system? So when searching on Google or shopping at Amazon, as you type in the search box, and one or more matches for the search term are presented to you. This feature is referred to as autocomplete type ahead and search as you type, or in criminal search, like this picture, presents an example of a Google search showing a list of the autocomplete results when you type some dinner into the search box. So search autocomplete is an important feature of many products. This leads us to the interview question, like design a search autocomplete system, or also call it design top K or design top K most search the query. So the first step is to understand the problem and establish design scope. So this one is from the Alex Su book. So the first step is to tackle any system design interview question to ask enough questions to clarify the questions requirements. Here is an example of the candidate interviews interactions. Candidates is the matching only supported at the beginning of the search query or in the middle as well. The interviewer says only at the beginning of the search query. And then candidate can ask some question like, how many autocomplete suggests should the system return? Interviewer 5. And how does the system know which 5 suggestions to return? Interviewer say, this is determined by popularity decided by the historical query frequently. Candidate say, does the system support spell check? Interview, no, spell check or autocorrect is not supported. And the candidate keep asking, any search query for English? Interviewer say yes. If time allowed at the end, we can discuss multiple language support. And candidate says, do we allow the capitalization and special characters? Interviewer say no, we just assume all search query have lower alphabetic characters. So second candidate says, how many users use the product? 10 million daily active users. Okay, so this is kind of like basic requirements. Here is a summary of the requirements. Fast response time as the user types a search query. Autocomplete suggestions must show up fast enough. An article about Facebook's autocomplete system reveals that the system needs to return results within the 100 milliseconds. Otherwise, it will cause this called what?
Stuttering.
Yeah, stuttering. Like I speak English, stuttering. Okay, stuttering. Relevant autocomplete suggestions should be relative to the search term. Sort means the results returned by the system must be sorted by popularity or other rank models. This is scalable. The system can handle high traffic volume. High available. The system should remain available and accessible when part of the system is offline. Slow down or experience unexpected network error. So this is a requirement. So for the estimation, normally you don't have the time, and so it will not going to mention about this part, but we can look into this. So assume the 10 million days active users, an average person perform 10 searches per day and 20 bytes of the data per query string. Assume we can use these characters in coding, and 1 character equal to 1 byte. Assume a query contains 4 words and each word contains 5 characters on average. So that is 4 times 5, 20 bytes per query. For everyday characters enter into the search box, a client send a request to the backend for autocomplete suggestions. On average, 20 requests are sent for each search query. For example, the following 6 requests are sent to the backends by the time you finish typing dinner, like here. So per second, users these functions, and the peak QPS is this large number, and assume the 20% of the daily queries are new, and 10 millions, right? This function, this means this one, 0.4 GB of new data is added to the storage daily. Okay, so what about the step 2? Step 2 is at the high level. The system is broken down into 2. Data gather system is gather user inputs, query, and this one is means
aggregates.
Okay, aggregates them in real time. Real-time processing is not practical for large data sets. However, it's good starting point. We will explore a more realistic solution in deep dive query service. Given the search query, we have the 2 give a search query or prefix and return 5 most frequently searched term. Okay, so data gather service. Let's use the simple example to show how the data gather service works. Assume we have a frequent table that stores the query string and is frequently as shown in the figure. Yeah, this is called figure. In the beginning, the frequency table is empty, and later the user enter the query like stuff is empty, right? And later the user query the Twitch and Twitter, and this one sequentially. The figure show the frequency of the table is updated here. You can see 1 time, 2 time, 1. And next we come into the query service. Okay, current picture is gone now. Whatever. Assume we have a frequently table as shown. It has 2 fields: query stored in the store, and then I think the picture is all gone. Okay, I will check later. So this is kind of like 2 services we need to do. This is kind of like a pick up with the top 5, so we can dive into deep here. In the high-level designs, we discussed the data gathering service and query service. The high-level design is not optimal, but it serves as a good starting point. In these sections, we will dive deep into a few components and explore optimization as follows: the try data structure, data gathering server, query server, scaled storage, try operations. So let's discuss about the try data structure first. And to better understand the try data structure, there are so many lead code problems can practice. It's a good way to understand the try. So let's see. Relational databases are used for store in the high-level design. However, fetching the top 5 search query from the relational database is inefficient. The data structure try prefix tree is used to overcome the problem. As try data structure is crucial for the system, we will dedicate significant time to design a customized try. So please note that some of the idea from the articles too, and the reference skip. And understand the basic try data structure is essential for this interview question. However, this is more of the data structure question than the system design question. Besides, many online material explain this concept. So in this chapter, we will only discuss an overview of the try data structure and focus on how to optimize the basic try to improve the response time. So try pronounced try. It's a tree-like data structure that can compactly store string. The name comes from the word retrieval, which index it is designed for the string retrieval operations. The main idea of the trie consists of the following. A trie is the tree-like data structure like this, and the root represents an empty string. It is kind of like an entry point, and each node stores the characters has 26 children, and one for each possible character to safeguard. We do not draw the empty links. So each tree's nodes represent a single word or prefix string. Figure show the trie with the search query like a tree, try, twi, wish, wing. Search queries are highlighted with the thicker border. So basic trie data structure store the character in the node to support sorting by frequency info need to be included in nodes. Assume we can have the following frequent table. Okay, so this picture, whatever. After adding the frequent info to nodes, right, update the trie data structure is shown in the figure here. You can say 25 means how many times the trie is show up, how many times they are queried. And how does the autocomplete work with the trie? Before diving into the algorithm, let us define some terms. P means the length of the prefix, and N means the total number of the nodes in the trie. This is how many nodes, 1, 2, 3, like N nodes. And C means the numbers of children of a given node. Like current here, children, like for this one, no, right? It's just to have one. So step 2, get top K most search query are listed below. Find the prefix, time complexity, and traverse the subtree from the prefix node and get all valid children. A child is valid if it can form a valid query string. Time complexity is OC. And sort the children and get the top K time complexity is where we're going to find and then return back. So it's the C log C. So let's use an example as shown in the figure to explain the algorithm. Assume K is equal to 2 and a user types the tr in the search box. The algorithm works as follows. Find the prefix tr, you can see find the tr, and traverse the subtree to get all the valid children. So in this case, node like tree 10 and choose 35 and try 29 are valid. And step 3 is to sort the children and get the top 2, and then return back. This is what we need. So the time complexity of this algorithm is the sum of time spent each step mentioned above, like OP and OC plus this one. So this algorithm is very straightforward. However, it's too slow because we need to traverse the entire trie to get top K results in the worst case scenario. Below are two optional optimization. Limit the max length of the prefix and cache top the search query at each node. And let's look at this optimization one by one. So we can limit the max length of the prefix, and the user really type a long search query into the search box such it is safe to say P is a small integer numbers, say like 50. Okay, so there is if we limit the length of the prefix, the numbers complexity for finding the prefix and can be reduced from the OP to the O1 time. Okay, the length of this one, we have some limit. So cache the top search query at search node to avoid traversal the whole trie. We store the top K most frequently used query at each node. And since the 5 to 10 autocomplete suggestions are enough for the user's case, relative smaller numbers. In our specific case, only the top 5 search queries are cached. So by caching the top search query at every node, we significantly reduce the time complexity to retrieve the top 5 query. However, these designs require a lot of space to store the top query at every node, and trading space for time is well worse, as its fast response time is very important. So this is figure, right? Figure show the updated data structure, and top 5 query are stored on each node. For example, the node with prefix stored in the following. You can see like for here 35 plus 29, and where the beer is 10. So let's revisit the time complexity of the algorithm after applying those two optimizations. Find the prefix node and time complex one, and return the top k. So we have the top k is already in here, so we can return directly. Since the top k query are cached, the time complexity for the step is 01. At the time complexity, as the time complexity for each of the steps is reduced to 01. Our algorithm takes 01 to fetch top the k query. So this is how it's improved but also it's a trade-off. You need 2 extra space to store the cache. Now we move into the next one. So what is the data gather servers? In our previous designs, when a user types a search query, the data is updated in real time. This appears not practical for the following 2 reasons. Users may enter billions queries per day, and per day updating the try on every query significantly slow down the query service, and the top suggestions may not change much once the try is built, thus it is unnecessary to update the try frequently. To design scalable data gathering service, we examine where the data comes from and how data is used. Real-time application like Twitter requires up to data autocomplete suggestions. However, autocomplete suggestions for many Google keywords might not change much on the daily, basis. So despite the difference in use case, the underlying foundations for data gathering servers remain the same, because data used to build the try is usually from the analytics or logging servers. So we can see here analytics log and a how do you pronounce this word? Okay, so how can aggregated data worker and updates weekly. You can choose the updates a month and update the try database, and then weekly snapshots of the database. So analyze logs is the stores raw data about the search query. Log that appears only and are not indexed. The table shows example like this. We have the query and what the user typing, and this is time. Oh, this one. Aggregators. It means the website or program that's collections related to items container and display them or link to them. Computing. And the size of the analytics logs is usually very large, and data is not in the right format. We need to aggregate data so it can be easily to process by our system. Depending on the use case, we may aggregates data different. For real-time applications such as Twitter, we aggregate data in a shorter time interval as real-time results are important. On the other hand, aggregating data is less frequently, say once per week. We might good enough for many use cases. During an interview sections, verify whether real-time results are important. We assume the rebuild weekly. Now we come in for here, aggregate date. The table shows the example of the aggregate weekly date time. Right? We have time field to represent the start time of the week, and the frequency is the sum of the concurrence of the concurrent query in that week. So we have the workers. Workers are a set of servers that perform a synchronized job at regular intervals. They build the trie data structure and store it in the trie database. Trie cache. The trie cache is the distributed cache system that keeps trie in memory for fast read. It takes a weekly snapshot of the database. Trie database. The database is persistent storage. Two options are available to store the date. So document store here. You can see, since a new trie is built the weekly, we can periodically take a snapshot of it, serialize it, and store the serialized in the database. Document store like MongoDB are good fits for the serialized date. Another thing is the key value pair. A trie can represent in the hash table like this by applying the following logic. Every prefix in the trie is mapping to a key in the hash table here. And the data on each trie node is mapping to the value inside. We can store top K words here. The figure shows mapping between the trie and the hash table. So in the figure, each trie node on the left is mapping to the pair on the right. And then if you are unclear how key value store refers to the table, okay, so just the key value pair here. So another is the query service. In the high-level design, the query service called the database, right? And directly to fetch the top 5 example results. Figure show the improved design as previous designs is inefficient. Load balance and cache try, right? A search query is sending to the load balance. The load balance route the requires to the API servers, and API servers get trie data from the trie cache, and the constructor automatically suggestion for the clients. If the cache we didn't find it, in the case the cache is not in the trie cache, we replenish back to the cache. This way, all the subsequent query from the same previous are returned from the cache. A cache miss can happen when the cache server is out of memory or offline. So query server requires the lightning fast speeds. We propose the following optimizations. Like for here, we have this is requires for the web application. A browser usually sending the AJA requires to fetching autocomplete result. The main benefit of the AJAX is that sending and receiving the required response does not refresh the whole page. Okay. Browser caching for many applications, autocomplete search suggests may not change much within a short time. Thus, the autocomplete suggest can be saved in browser cache to allow subsequent requires to get the results from the cache directly. And the Google search engines use the same cache mechanism show the response header when you type system design interview. On the Google search engine, as you see, Google search the results in the browser for 1 hour. Please note, priv in the cache means results are intended for a single user and must not be cached by a shared cache. And for the message is this one. It means the cache is valid for the 3,600 seconds, aka an hour. So data sampling for a long scale system. Scale system. Logging every search query requires a lot of processing power and storage. Data sampling is important. For instance, only 1 out of every n requires is logged in by the system. So we have the try operations. Try is the components. Core. Try is core components of the autocomplete system. So let's us looking at how the try operations. We have the create, delete, update, delete work. So we have the create. The try is created by workers using the aggregate data. The source of data is from the analysis log database. So we can see here we have worker to build the try and store in the database. I will talk about this later. So this is create and update. There are 2 ways to update the tries. Option 1, update the try weekly. Once a new try is created, the new try replaces that old one. So you can see this one is B and this is just the update here, right? Bear 30 and bear 30 update here. Update in individual the try nodes directly. We try to avoid this operation because it's slow. However, if the size of the try is small, it's an acceptable solution. When we update a try node, its ancestors all the way to the root, but must be updated because ancestors store the top queries of the children. You can see here, if I update here, this one is also update, this one is also update. Yeah, this picture shows an example how the update operation works. On the left side, you can see you query the bear. Has original value is 10, and on the right side is update to the 30. As you can see, the node and its ancestor has ancestor here bear. The values update to 30. So what about the update delete? We have to remove hateful, violate, sexual, this call it explicit, or dangerous autocomplete suggestions. We add a filter layer in the front of the try cache to filter out unwanted suggestions. Having a filter layer gives us the flexibility of removing the resource based on the different filter rules. Unwanted suggestions are removed from the physicals from the database, asynchronized, so the correct data set will be used to build try in the next update cycle. The database is a synchronized update to remove hateful content. So this is how it works. So what about the scaled storage? Scaled storage. Now that we have developed a system to bring autocomplete query to the user, it is time to solve the scalability issues when the try grows too large to fit in one servers, right? So since the English is the only support language, a naive way to share it is based on the first characters. So here are some examples. If we need 2 servers for the storage, we can store queries starting from with the A to the M on the first server. And for the second server is the N to Z on the second server. If we need the 3 servers, we can split the queries into A to I to J to R to S to Z. Following this logic, we can separate the query up to the 26 servers because there are 26 alphabetic characters in English. Let us define the sharding based on the first character as first level sharding. To store the data beyond the 26 servers, we can share it on the second or even at the third level. For example, data query that starts with the A splits 4 servers, right? For here. At the first galaxy glance, not galaxy. Okay. At the first glance, this approach seems reasonable until you realize there are a lot of more words that start with the letter C than X. This creates uneven distribution. To mitigate the data imbalance problem, we analyze the history system distribute pattern and apply the smaller shadowing logic, right? Like showing these pictures. The shadow map managers maintain a lookup database for identifying where the rows should be stored. For example, if there are similar numbers of the historical query for the S, for those sort of things are combined, we can maintain two shadows, right? One S for the S and one for the U to the Z, to see what shadow it is. Then it's got something and retrieve data from the database. Now we just need to wrap up. So after you finish this deep dive in your interview, might ask you some following up questions. How do you extend your design to support your multiple language? To support other non-language query with Unicode characters in TriNote. If you are not familiar with Unicode, here is the definitions. An encoding standard cover all the characters for all the writing system of the word, modern, and this is called what? Ancient. So interviewer say, what if top search query is in one country are different from others? In this case, we might build different tries for different countries to improve the response time. We can start tries in the CDNs. Interviews say, how can we support the trending real-time search the query? Assume a new event breakout, a search query suddenly become popular. Our original designs will not work because offline workers are not scheduled to update the try yet, because this is scheduled to run a weekly basis. Even if it is scheduled, it takes too long to build a try. So build a real-time search autocomplete is very complicated, and it's beyond the scope of this book, so we will only give a few ideas. Reduce the work date set by sharding, and change the rank model and assign more weight to recent search query. And date may come as streams, so we do not have access to all the data at once. Streaming date means the data is generated continuous. Streaming process requires different set of systems, like Hadoop MapReduce. And this Hadoop MapReduce is based on the Google distribute system. There's a paper on this. And Spark, right? So because all those of top require specific domain knowledge, we're not going into detail here. So yeah, you can, congratulations, finish here. Okay, so what we gonna do here? This is the whole picture about this one. So let's start from in this way. That is, previous is very long detail, and for here is very short. So what is the search autocomplete Google suggestion, right? You can see here, this is Google suggestion. So let's start going to here. What is the functional requirements? We need to return the autocomplete suggestion and the user type, right? This function, these requirements, what we need to satisfy. Prefix match only, and return top case suggestion. Results ranked by popularity, keystroke frequent, English lower, right? And no spell correction. And for the non-functional requirements, latency, handle very high QPS, and scarce storage, compute, and high available. And for the con entities, we need some like prefix, suggestion, scorn, like this is keywords. And for the offline analysis side, we have some events, some information to tracking what the users query. And for the API design, we have the autocomplete API is get, when people type in something and it will get something. And the response is like this, prefix is what, and for the how many top K and suggestions, and whether it's cached somewhere, some details were stored inside. And for this one is for the log. And when the user type in the specific query, it will have the log for the future tracking. So let's see how it's designed here. So for the high-level designs, we start from the user, and it will send in the requires typing the query search, and it will go to the load balance. And at the same time, so when this is a log, and it will store what the user is doing, and then aggregator, and that for here, and for the builders will update the tries for the every weekly. So this is for the log API. And what about the get API? For here, loading the balance, right? And then API servers will calling to get to checking the user something, whether in the cache, the try whether it exists in the cache. If not, we just need to go to the original try database to figure out what happens, and then return back to the user. So this is high-level design of here. So what is another thing is the try data structure. So it's look like root. This is empty strings when the users want to, this is the characters. And for the characters, we have the specific words. Like for here, true is word and true. So we have to, normally in the analytical problems, when you design the node, you have to check or current node whether it's the word or not. So you better to add the Boolean point inside. Our current here is a root. So you can see, and also based on when you're searching on this, right, and then you can figure out this. We will have so many rules and information, and you can figure out like top 2 is what kind of this one, and then return back. And for the better way to, because this one, every time you search something, you have to track in all the tree. So to improve the performance, we better to, when we create the tree, so it will also update the cache, like current cache, right? You can see this is what cache is stored, like true 35 try something. So if you want to find out like how many top K, so you can directly to get this one. So it just need all one time, no need to search in the button again and again over time. So this is the try data structure. So let's talk about the high-level design here. We have the user balance, right? So for here, for the latency here, we can add more cache. Original, we don't have the, we have the cache, but we don't have the multiple layer. We can level 1, level 2, and then it will get more quicker response. So what about the handle very high? So this balance can help us to doing this. So what about the scalable storage and compute? For here, we can divide it not just only one cache, we have two multiple layers cache. And also we have the shared mapper manager, right? Because the database, we can put the lots of information based on the index into the different database. And for here, it's kind of like tier the requires or which you wanted those information, which database you can go, then return back. So this is the way. And for the high available, we can use the like duplicate way. Duplicate, if this one is shut down, with there it works fine. So because we have a duplicate database, then it's just called the duplicate one, and then it still works fine. So this is high available. Yep, thank you.